Hello, everyone. Once again, thank you so much for your time. Today, I'd like to continue on our discussion on signal representation. Today's discussion, in fact, is a request by you guys. Someone dropped me an email to ask me for a detailed example how we can actually make use of Fourier series to represent a complex periodic signal. So today, I'm going to give you another example with more illustration. How can we actually exactly use this Fourier series to represent a complex periodic signal? Today's discussion will be the part 5 series discussion. The earlier on series discussion, I have put the video link under the description. So please go through the video if you're keen to know more about signal representation. This is my email. If you have any question regards on today's discussion, please drop me an email. Before I continue, I'd like to urge you guys to support this channel by pressing the like and subscribe buttons. Please also turn on your notification bell in order to receive more information from this channel. Thank you so much. So today we are going to do another example 4. Okay, the Fourier series equation for the Sawtooth waveform is actually governed by this equation. So we are given that the E is equal to 3 volt and the period is 0.1 millisecond. So we are tasked to sketch the amplitude spectrum of this signal. Okay, so let's see how can we approach this question. Okay, so this is what I have discussed with you on the previous slide. So basically, I put them together in order to obtain some of the essential parameters that we need. Like what I mentioned, the E is given to us, the T or the period is given to us, which is 0.1 millisecond. From here, I can compute my frequency. Okay, the frequency is equal to 1 over period. Okay, so this period is 0.1 millisecond. So from here, I compute that the frequency is 10 kilohertz. Okay, we actually can conclude that this is the fundamental frequency. Remember this, the fundamental frequency is always the lowest frequency. So this is what I have shown to you. The fundamental frequency, you actually can look based on the waveform, the period, and from the period, we can actually calculate the frequency, and hence, this is how we can obtain the fundamental frequency. Next. Okay, so let's take a look on the equation here. Okay, so for example, we already found the fundamental frequency, which is 10 kilohertz. Okay, from here, you can see that this is the fundamental frequency. We have the second harmonic, the third harmonic, and the fourth, fifth, sixth, seventh harmonic, etc. Okay, so from here, you can see that earlier on example 2 and 3, okay, basically they don't have the even harmonic. But for this Sawtooth, they actually have the even harmonic. So we need to consider the even harmonic for this case here. You can see from here, this is the even harmonic. This is the even harmonic. Second and fourth harmonic. This is the fundamental. This is the third harmonic. And from here, we can compute the harmonic frequency. The second harmonic having a frequency of 20 kilohertz. The third harmonic, which is 3 times 10, which is 30 kilohertz. Same wise for fourth harmonic, which is 4 multiplied by 10, which is 40 kilohertz. So now let's work on the amplitude. Okay, so the fundamental frequency, basically the amplitude is 2e over pi. Okay, the E is given in the question, which is 3 volt. So what I need to do is basically 2 times 3 divided by pi. So this is how we obtain the V peak of the fundamental frequency, which is 1.9 volt. As for the second harmonic, okay, you can see from here is basically 2 times E divided by pi multiplied by 1 over 2. So in short, you can cancel away the 2, okay, which means that it's E over pi. Okay, if not, you can do this. Okay, so these two, like what I mentioned, you can cancel away. But from here, you know that it's simply just E over pi. Okay, E is given in the question, which is 3. So I can actually work out, which is 0.95 volt here. Okay, so this is the V peak for the second harmonic. Same wise for the third harmonic. Okay, from this equation, I can see that it's basically 2e over 3 pi. Okay, so I can actually do this 2e. Okay, E is 3 volt over 3 pi. So I punch my calculator. Okay, I should be able to get this 0.64 volt. Finally, on the fourth harmonic, Okay, so from the fourth harmonic, I can see that it's simply 2e over 4 pi. So I can actually punch this 2e over 4 pi. So I can punch my calculator, okay, which result the fourth harmonic having the amplitude of 0.48 volt. Okay, so basically I have obtained all the parameters and I'm ready to draw the amplitude spectrum. This is the table that I've done on the previous slide. So like what I mentioned to you, I'm ready to draw the amplitude spectrum. Okay, firstly, this is the fundamental. They have this 10 as the frequency and they have this peak amplitude of 1.9 volt. So this is for the fundamental frequency. Second harmonic, 20 and 0.95. So at 20 kilohertz, okay, I have a V peak of 0.95. Same wise for the third harmonic, okay, they actually happen at 30 kilohertz, having a V peak of 0.64 volt. And last but not least, the fourth harmonic, okay, the V peak is equal to 0.48. Basically, I'm done for the amplitude spectrum. Okay, so from here, you can see that I actually transform from the equation, okay, into an amplitude spectrum. Next, the Sawtooth waveform is fed to a bandpass filter, okay, which has a response as shown in the figure below. Sketch the signal at the output of the bandpass filter in frequency and time domain. State the mathematical equation of this output signal. Okay, so this Sawtooth signal, okay, what they do is basically they pass through this bandpass filter. So what will be the output of this bandpass filter? Okay, let's take a look over here. So basically they have these characteristics of the bandpass filter. Basically they can only pass the frequency component from 15 to 25 kilohertz. So this is what we have done on the amplitude spectrum on the Sawtooth waveform here. So from the question given to us, 15 to 25 kilohertz will be able to pass. We show that 15 to 25 can pass. We show that I actually can only pass through 20 kilohertz. The rest of them will be antennated away by the bandpass filter. So right at the output of the bandpass filter will be simply just one frequency component having a frequency of 20 kilohertz with a V peak of 0.95. So I hope this is clear. So this is the resulting that can so-called pass through the bandpass filter with only one frequency signal as explained. Okay, so from here, I'm ready to draw the time domain and also the equation. Okay, firstly, I can done the equation first. Okay, so from here, this is the fundamental frequency, 2 pi f. Frequency is 20 kilohertz. So they have a V peak of 0.95. So this is the equation in time domain, okay, that basically describe the signal at the output of the bandpass filter. Next, from here, I also ready to draw the time domain. Okay, so this is a sine wave. So I draw a sine wave. Next, here I know that they have a V peak of 0.95. So basically they have a DC of 0. Okay, so the V peak is actually 0.95. So I can draw this waveform. And last but not least, I can furnish the period. Okay, I have the frequency, which is 20 kilohertz. From here, I can compute that the period is 50 microseconds. So from here, you can see that I'm done on this example 4 by transforming them from amplitude spectrum, go through a bandpass filter. Finally, what can be at the output is simply just one frequency component with a time domain as illustrated here. Okay, so I can do a very quick conclusion over here. So this is a Sawtooth signal that is fed at the input of the bandpass filter. The bandpass filter has this filtering characteristics. They basically pass anything that is within 15 to 25 kilohertz. So from here, I have worked out that this is how they look like as an amplitude spectrum here. They in fact consist more than fundamental, second, third, fourth. In fact, there will be fifth, sixth, seventh, etc. Okay, but what happened here is basically this frequency response pass through this bandpass filter. Only 20 kilohertz will be able to result at the output of the bandpass filter. The rest of them will be antennated away by this bandpass filter. And from here, I also show how can I draw the time domain based on the previous slide. Okay, so basically this is an example for a sawtooth that is represented by a Fourier series. I use the Fourier series equation to transform them into amplitude spectrum. I pass them through a bandpass filter. The bandpass filter basically has certain characteristics. They basically allow a specific band to pass. And from this particular example, they only allow the frequency component at 20 kilohertz to pass. And therefore, from here, I can also draw the resulting signal in time domain. Okay, so I'm done on this example 4. Let's do a very quick recap on this periodic signal. As I mentioned to you earlier on, the periodic signal can be actually called a simple signal or a complex signal. For a simple signal, they simply only has one frequency component. Okay, having one frequency component means that they basically look like a sine wave in a time domain. So this is what you mean by a simple signal. They only has one sine wave, and on frequency domain, they only have one frequency component. So this is what we classify as a simple signal, one frequency component. As for complex signal, okay, in short, like what I mentioned, basically they contain more than one frequency component, or they have many frequency component. Okay, for example, we have this square wave, we have this triangular wave, we also have the sawtooth wave. They basically lump under this complex periodic signal. Okay, in frequency domain, you will be able to see that they are actually represented by many frequency components. And the spacing between the frequency component is simply just an integrate multiply of the fundamental frequency. With this, I'd like to stop my discussion. Please help to like and subscribe. Thank you so much.